Namaste dosto. Imagine you're trying to find the height of a tall tree without climbing it. How do you do that? This is where the fascinating world of trigonometry comes in. The very name trigonometry comes from Greek words trigonon, meaning triangle, and metron, meaning measure. So it literally means measuring triangles. Trigonometry is the branch of mathematics that studies the relationships between the sides and angles of right-angled triangles. But why is it so important? Well, because these relationships let us connect angles, which are measured in degrees, with the actual lengths of sides using special functions like sine, cosine, and tangent. These trigonometric functions bridge the gap between angular quantities and linear distances. That's why trigonometry is fundamental not only in geometry, but also in fields like astronomy where we calculate distances to stars, physics where we analyze waves and oscillations, and engineering applications including satellite positioning and mechanical design. For example, when surveyors measure land or engineers design gears, they rely on these trigonometric relationships to translate angles into practical measurements. The ratios defined by trigonometric functions give us a powerful algebraic way to solve problems that depend on angles. And this blend of geometry and algebra is what makes trigonometry so versatile. On this slide, you can see a right-angled triangle with one angle marked as theta. The side opposite to theta is called the opposite side, the side next to it is the adjacent side, and the longest side across from the right angle is the hypotenuse. Don't worry, we'll dive deeper into all these terms soon. So, in short, trigonometry helps us measure and understand angles and sides, making the impossible, like measuring a tree's height from afar, entirely possible. Arey vah! Ready to explore how these side names help us define the ratios? Let's move to the next slide. Continuing from our triangle ABC with angle theta, let's dive into the stars of today's show: sine, cosine, and tangent. Here's how we define them. Sine of theta is opposite over hypotenuse, that is, side BC divided by AC. Cosine of theta is adjacent over hypotenuse, so ab over AC. And tangent of theta? It's opposite over adjacent, BC divided by ab. So, sine and cosine compare a side to the hypotenuse, the longest side, while tangent compares the side opposite to the side adjacent, sort of like comparing the perpendicular height to the base. But a quick warning, these ratios only make sense when their denominators aren't zero. For example, tangent is undefined if the adjacent side length is 0, because division by 0 is a no-go. Here's the cool part. No matter how big or small you make your triangle, as long as the angle theta stays the same, these ratios remain constant. So, these trigonometric ratios depend solely on the angle theta, not on the triangle's actual size. Shabash, that's a powerful idea. Shabash. Now you're ready to meet the 6 trigonometric ratios that rule this mathematical world. The 3 primary ones are sine, cosine, and tangent. But there are also their 3 reciprocals: cosecant, secant, and cotangent. Let's take them step by step. Remember a triangle? For an angle theta, we have this: sine of theta is opposite side divided by hypotenuse. Cosine of theta is adjacent side divided by hypotenuse. Tangent of theta is opposite side divided by adjacent side. So, spoken out loud, sine theta equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse, and tangent theta equals opposite over adjacent. Easy to remember because each relates to sides in a unique way. Now, what about the reciprocal ratios? These are just the upside-down versions. Cosecant of theta is 1 divided by sine theta. Secant of theta is 1 divided by cosine theta. And cotangent of theta is 1 divided by tangent theta. Arey vah! We understand now how these ratios are defined. But have you ever wondered what's their maximum or minimum value? The answer lies in the geometry of the triangle itself. Because the hypotenuse is the longest side, both sine theta and cosine theta must always lie between 0 and 1. Formally, sine theta is greater than 0 and less than 1. The same goes for cosine theta. This means these values never go below 0 or above 1 for any angle between 0 degrees and 90 degrees. What happens when theta is very small, almost 0 degrees? Sin theta approaches 0. Since the opposite side is tiny compared to the hypotenuse, while cosine theta gets closer to 1 because adjacent side nearly equals the hypotenuse. Conversely, as theta moves close to 90 degrees, sin theta grows toward 1. Because the opposite side nearly equals the hypotenuse, and cosine theta shrinks toward 0. Now, tangent and cotangent ratios behave a bit differently. They can become very large or very small, even tending to infinity, because they involve division by sides that can become very close to 0. For example, tangent theta is opposite over adjacent. If adjacent side gets extremely small, tangent skyrockets towards infinity. Understanding these boundaries helps us know which angles produce meaningful ratios and where functions may not be defined. It's crucial for applying trigonometric ratios safely in problems or models. On your screen are graphs showing how sine, cosine, and tangent change as theta goes from 0 degrees to 90 degrees. The curves tell their story clearly. And aren't they beautiful? So, how do we remember the values for angles we use all the time? That's coming up in the next slide on standard angle values. Excellent, beta. Now let's talk about some special angles that pop up everywhere. 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Knowing the sine, cosine, and tangent for these angles saves you loads of time in exams and calculations. For example, sine of 30 degrees is 1/2, meaning the opposite side is half the length of the hypotenuse. Similarly, cosine 60 degrees is also 1/2, which is no coincidence. In fact, sine 60 degrees equals cosine 30 degrees. This is because of the symmetry in triangular shapes. The tangent of 45 degrees is exactly 1. This is because in a 45-45 right triangle, the opposite and adjacent sides are equal in length. Namaste once more. It's time for some algebraic magic derived from the Pythagorean theorem. Remember, in any right-angled triangle, the square of the opposite side plus the square of the adjacent side equals the square of the hypotenuse. In symbols, it's opposite squared plus adjacent squared equals hypotenuse squared. By dividing each term by hypotenuse squared, we get a very important trigonometric identity. Sine squared theta plus cosine squared theta equals 1. Saying it fully, sine squared theta plus cosine squared theta equals 1. This is the king of all trigonometric identities. It lets us rewrite many expressions and is the backbone of trigonometric problem solving. Similar divisions give us two more identities. 1 plus tangent squared theta equals secant squared theta, and 1 plus cotangent squared theta equals cosecant squared theta. You're doing great. Now, here's a cool fact. All right triangles that share the same angle theta are similar triangles. This means their corresponding angles are equal, and their sides are in the same proportion no matter the size. Because of similarity, the ratio of the opposite side to the hypotenuse, or sine theta, is always the same for that angle. It does not depend on how big or small the triangle is, only on the angle theta itself. The same goes for cosine and tangent. Their ratios are fixed for a given angle. This is why trigonometric functions depend only on angles and not on the dimensions of the triangles. This powerful idea justifies defining sine, cosine, and tangent not merely as ratios in a triangle, but as functions of an angle. No matter where you see the angle theta, in circles, waves, or rotations, these ratios remain consistent. On the screen, observe how two similar right triangles with the same angle theta keep their respective sides proportional. This visualizes why the trigonometric ratios are constants for an angle. So remember, the magic behind trigonometry's power is the similarity of triangles. Ready for a quick summary to lock all this in? Let's quickly recap what we've learned today. We began with understanding trigonometry as the study of right triangles, connecting sides and angles through neat ratios. Our key formulas are sine theta equals opposite side over hypotenuse cosine theta equals adjacent side over hypotenuse, and tangent theta equals opposite side over adjacent side. Don't forget the reciprocal ratios. Cosecant theta is 1 over sine theta, secant theta is 1 over cosine theta, and cotangent theta is 1 over tangent theta. From the Pythagorean theorem, we have the beautiful identities: sine squared theta plus cosine squared theta equals 1. 1 plus tangent squared theta equals secant squared theta. And 1 plus cotangent squared theta equals cosecant squared theta. Key ideas. Trigonometry relies on right triangle geometry but extends into an angle-based framework thanks to similar triangles. This means these ratios are fixed and consistent for a given angle.